cuando se hacía la velocidad, casi no. Todavía sí. Entonces, déjame voy a hacer el micrófono a hablar, a ver si nada más hay que actualizar la vamos a estar escuchando.
El internet está reproduciendo.
Sin transmitir.
Es que ya le estamos transmitiendo.
Pero no sabemos si
Se está reproduciendo en YouTube.
porque no hay nadie que lo pueda ver porque no tiene conexión a internet.
Después, entrar y quitarlo rápido. Pues, así. Sí, un poco.
¿Tienes web? Entra a YouTube, busca el, ¿cómo se llama? Quantum Statistical.
Basic Seminar. Si no, aquí también lo puedo ver.
¿Qué más? ¿Tienes web?
No, sí se está escuchando.
Entra a YouTube, busca.
Ok.
¿Sí?
Sí, cuando quieras.
Ok. Okay, welcome to our quantum and classical statistical seminar. Today we have a talk from Dr. Alonso Castillo. He is a professor at the Department of Mathematics here in the University of Guadalajara and obtained his bachelor degrees in mathematics here at the University of Guadalajara. And he did his master's and the PhD in mathematics also at the Imperial College of London. He was a postdoctoral researcher at the University of Zaragoza in Durham University, and currently he is a member of the STEAM Level 2. His research interests are in group and semi-group theory, non-associative algebras, and theory of cellular automata. So it is my pleasure to introduce you to Dr. Alonso Castillo, and please.
Thank you very much. Thank you. So, yes, well, today we'll talk to you about cellular automata over groups. So, probably many of you are familiar already with cellular automata. In this talk, I'm more interested in the theoretical point of view. So, I don't really work so much with applications or modeling and stuff like that. I work mainly with the theory, but so in this talk, I will try to convince you that there is a rich and strong theory about the cellular automata, and that it has actually deep connections with group theory. So just to have a flavor of that. So very briefly, just like a bit of history, cellular automata were introduced by John Paul Neumann and Ulam in the 1940s. And what they were working in the Los Alamos National Laboratory in the problem of self-replicating systems. So they were thinking actually if it was possible, let's say, to create a robot that replicates itself and stuff like that, right? This kind of theoretical question. But well, as von Neumann said, there's no sense in being precise when you don't even know what you're talking about. So we'll see with more precision what is this about. So I started working in this area thanks to this book. It's called Cellular Automata and Groups from 2010. Actually, the second edition is coming this year, at the end of this year. And basically, this book has a very rigorous treatment of cellular automata and its connections with group theory and topology and these other areas. And it's finally where I felt like comfortable studying them, because I was interested in this topic, but sometimes when I was checking a computer science reference or I don't know, physics reference, stuff like that, because my background is more in mathematics, I was not really following very well. I was not understanding very well. And finally, when I found this book, so this is very recommended if you want to learn about this theory of cellular automata, the foundations. So in general, this is more or less the general setting that we will be talking about. In general, a cellular automaton is going to be a special kind of function that goes from this space, the A to the G, to A to the G. And A to the G, we call it a configuration space. Yeah. So in this case, A is going to be a set, and G is going to be a group. I'm going to define exactly what is this configuration space, but think of it as a function that between this in this set, right? That maps from this set to this set. And it has a special feature that it is defined via a local function, A to the S, where S is just a finite subset of the group called a memory set. So this is kind of the key property that I'm going to go into more details now. This is just to have a general reference of where we are going, right? So to begin with, I want to talk a little bit about this configuration space, A to the G. So what it is and what properties it has. Well, this main configuration spaces actually maybe is not universally called like this. At least in this book of cellular automata and groups, it's called configuration space. But sometimes there are other mathematicians refer to completely different space. They call them configuration spaces as well. So anyway, in this context, we are going to call this configuration space. So the configuration space is going to be this set, A to the G, and it's the set of all functions from G to A. G is a group, can be finite, infinite, I don't care. You can think of it as a discrete group, right? We don't care about that topology in this group now. And A is any set that we can call an alphabet, or you can think of A as a set of colors, for example, right? So these functions, what they are doing is that to every element of the group, they're assigning a color, or they're assigning a state, or they're assigning a letter of the alphabet, right? It's a set of all these functions. And the notation is because actually the Cartesian power of a set is formally defined like this, in the set of functions that goes from here in the exponent is the domain actually of the functions, and this is the domain of the function. This is like a notation in mathematics because it reminds us of the sort of a Cartesian power, right? And this is how it's formally defined, the Cartesian power as the functions. So for example, when the group is the integers set, the space A to the set, we can think of it as by infinite sequences of this form. So for example, if you remember from classes in analysis or calculus or at some point that you have studied, we study real sequences, right? So a real sequence is a function from the natural numbers to the reals. So they progress. You have, let's say, x1, x2, x3, etc. In this case, because the domain is all the integers, the sequence is indexed by all integers. So we are going from minus infinity and all the integers, and -2, -1, 0, 1, 2, and we progress. Right. So this is what we mean by infinite sequences. It's a convenient way of looking at the elements. So one by infinite sequence is going to be one function, the configuration space. Yeah. And okay, if you have any questions, you can interrupt me at any time. Okay. So for example, when the group is set square, then the space A to the set square, we can think of it as the set of all colorings of our rectangular grid. So this would be a particular configuration in A to the set square. Here we are assuming that A has two colors at least, white and black, for example. Of course, this is infinite, right? It goes here. I cannot show it here. So the thing is that the group has pair of integers, so the grid represents this, right? So around here might be the point 0, 0, and then we have 1, 0, 2, 0, etc. And this is how the grid is formed. And to each element of the grid, we're assigning a color. In this case, black or white, etc. So when you have other groups, you can visualize it in different ways, perhaps, in these configuration spaces. Okay, so another interesting thing of this configuration space is that there is a group action on the configuration space. There's like a natural group action of the same group G over the configuration space A to the G. And the action that we are more interested in is the shift action. So the shift action is defined like this. This is a group action in the formal sense, right? In the formal sense of a group acting on a set. And basically, this is telling us that when you have X is a configuration, and you apply G, G dot X is going to be again an element. It's going to be another configuration. And how is this configuration defined? Well, if we see the H coordinate, let's say, of the configuration, of the value at H, is going to be given by this. It's going to be the same as X, but shifted by G inverse, actually. Here, G inverse, we have to put their inverse because of technical reasons. If the group is abelian, you don't have to put the inverse. So in many cases, in many applications, when we work with the integers or with set squared or with other abelian groups, you can put here G and everything is fine. But if the group is non-abelian and we want to work with in a general setting where G is any group, then because of technical reasons, you have to put here G inverse to actually prove that this is a group action. Well, this is just a brief reminder. With an action, we can define here the orbit and the stabilizer, but actually I'm not going to use that very much. Okay, so this is how the shift action behaves on A to the Z. So by definition, we have these, right? And remember here, in this case, X, you can think of it as a bi-infinite sequence. So we have a bi-infinite sequence, and then you act by an element K, by an integer K. So this new bi-infinite sequence is going to be the same as X, but shifted by K. So this diagram, in this diagram, we can see things better. This is the original sequence, X. And if we act, let's say, by 1, the thing is, where we have the index 0, now we have the index -1 because of this rule here, right? Where we have the index 1, we will have now the index 1 minus 1, which is 0. Here we will have 2 minus 1, which is 1, etc. So at the end, physically, you can see that the sequence kind of moves towards the right, right? We have here x0, and everything moves one step towards the right. Yes?
Why you are defining it as a new sequence? Because it's bi-infinite, right?
Yes.
Direction is goes to infinity. So if
Yes.
you shift it or not, it should be the same sequence.
Yes. So this is kind of the idea of defining this action, because formally it's not going to be the same sequence because there are different functions, right? They have different values in the position. So in these sequences, we care which one is the first position, which one is the second position, which one is the nth position.
Yeah, but your position in that sense doesn't make much sense if it's infinite. But
Yeah.
what?
Yeah. I mean, the idea is the point is, let me tell you this, right? So we have x formally. What it is a function, right? So these things as functions are going to be different because when you evaluate it in different elements here, they give you different values. But what we do with the action is kind of identify them. We identify them in the same orbit. We say, okay, maybe it's the same sequence, but you shift it and we don't care. It's going to be the same orbit, right? For example, let me tell you, if you suppose here, if you evaluate x at position 0, it will give us x 0. If we evaluate 1.x at position 0, it will give us x minus 1. So formally, I mean, these could be different symbols, right? Depends what sequence we're taking. But we can take a more explicit example. Let's say, well, this doesn't work very well. But we can take a more explicit example. We can take x, let's say, all zeros, and then just a 1 here. Okay. Thank you very much. Thank you.
I think it's clear, right? I mean, if you look with the camera to a certain interval and you then this sequence will.
Yes, very good.
Right?
So for the finite size, it's a different sequence. But if you, it's just like renormalization. You will go backwards to with your camera, you see the same sequence.
Yeah.
You don't, it's just taking the origin. My point is that if it's a finite sequence, then definitely it's a different sequence by safety. But if it's an infinite one, I don't get it how it will be.
I think that depends basically on the value of k, right? How much do you shift?
If only if the k scales with your
The way you're zooming out.
Yeah. Scales with this the way you are observing it or the size of the sequence, then only it matters. If the k is finite, then I don't see how it is.
Just look at the element 0, right?
Yeah.
And you see that it changes. So
Yeah, but if you
something
go
was-
backward,
No, but
it's just it's an infinite
I
sequence.
understand, but maybe you don't want to go backward. You want to look at the
Yes,
element.
It constant is invariant over the action of the group, right? But it has to be like that, or is that special case?
Because you are taking the whole set, that's invariant.
Sorry, if what is invariant?
The set over the action of the group,
It's invariant, yes, but by the definition of the action,
it doesn't have to be.
it's sort of invariant. You take a by infinite sequence, you apply the action, and you get another by infinite sequence. So in that sense, it's invariant. Among the by infinite sequences, you can have other invariant subsets, for example. So the thing is, I think it's just a matter of kind of notation,
Okay, so
formalism.
what I'm uncomfortably
Yes.
with is this that you are calling it a different sequence for a by infinite sequence. If it's a by finite, my point is if it's a finite sequence,
Yes.
then I have no trouble.
Yes. Okay. No, yeah, I understand. The thing is that formally, if we look at them as functions, forget they are sequences. Sequences are a representation of the function, right? But what they really are mathematically, it's that they are functions. So as functions, they are different, right? Because the values of when you evaluate it in the domain, they might give you different values. So for example, we have here, and then we have 1.x equals 0, 0, 0. Sorry, here, moves 1, 0, 1, 0, 0. Right? So the thing is that this representation of sequences remembers the positions. It remembers that here was the 0th position. It remembers that he was 1, 2, minus 1, minus 2, because they are not sets. They are formally functions. So they remember the positions that you are. So these are formally different things because simple as that, when you evaluate it in different values of the domain, it gives you different answers. The function gives you different answers. So intuitively, what we want to do with this action is to say, okay, we want to identify it and they want to be the same as you think, right? We want them to be, we don't care if the one appears here or the one appears here or the one appears a bit later. So formally what we do is that we can take the orbit of X. So the orbit of X now is going to be the set of all shiftings of X. And now this is, I think, what you have more in mind, the sort of the orbit under the action. We consider this as now, if we identify the sequences as orbits now, then this is indeed the same. This represents the same orbit and the same orbit, so they are sort of the same sequence. But when we go sort of to the formal definition as functions, they are different. Okay. Okay. Well, thank you. Well, now let me just say a little bit about there's another important structure in this configuration space that is it has a topology. So it has we consider it with the product topology of the discrete topology of A. So the discrete topology is something very boring, as you know. It's just all the subsets are open, so it's kind of trivial. But when you consider the product topology of a discrete topology, especially if the group is infinite, then you get something that it's not a discrete topology. Again, you get something that they call a pro-discrete topology. So some characteristics of this pro-discrete topology is that, for example, is the coarsest topology with the fewest open sets, on which these projections, these are sort of the projections. You take a configuration here and you evaluate it in a particular G, in a particular element of the group. These projections are going to be continuous. And a basis for this topology are these sets here. So a basis means that basically every open set of the topology can be seen as a union of these guys. And basically what this is telling you is that we can sort of fix this intuitively. This is going to be telling us you can fix some values on Y, on the configurations at a finite subset S. And then you can say, give me all the configurations that have these particular values at these particular positions. So let me write here an example. So it's more, so for example, we can consider, let's say, all sequences going back to this scenario. So here we don't care what it has. I'm going to put an asterisk, and I want to have 1 and 0. For example, this is the coordinate 0, this is the coordinate 1, and here I don't care what it is. So this is going to be an open set, right? I mean, I'm very bad with the notation, I'm sorry, but I hope it's understandable. So what I mean is this is the set of all sequences such that in these parts of the sequence, it can be whatever value you want, but in the 0th position and in the first position, in the 0th position is going to be a 1, and in the first position is going to be a 0, right? So I'm kind of specifying, fixing some values in a finite number of positions of the sequence. And here the important thing is it has to be a finite set. Yeah. So this is going to be an open set in the topology. Yeah. Okay. Actually, this is not invariant in case this open set is not going to be invariant in the shift action, but there are some open sets that are invariant as well. Okay. So some other characteristics, some technical characteristics of this topology. For example, this is going to be always a Hausdorff space, and it's going to be totally disconnected. And moreover, it's going to be compact if and only if the set A is finite. Actually, this for the case of A to the Z, for the ones of you that have read more about topology, it turns out A to the Z is homeomorphic to the so-called Cantor space in topology that you can construct with the real numbers and all this. It's going to be the same, basically, that this space. Well, you can take the alphabet 0, 1, and then you take the Z. This is A, right? In this case, A is just going to be 0, 1 to the Z. This is the same as it's going to be homeomorphic to the Cantor space. And then, well, finally, another property of continuous functions here is that a function of this space A to the G to A to the G is going to be continuous in the topology, right? In the topological sense, that means that the pre-image of any open set is going to be open. It's going to be continuous if and only if the composition with the projections is continuous for all the projections. So this, you can make an analogy, let's say, with vector calculus, vector analysis, that you know that a function from R to the N to R to the N is going to be continuous if and only if the coordinate functions are continuous. This is sort of the same, right? Because these things here are the coordinate functions, actually. So it's telling us the same. So here I have a little proof. Maybe, I don't know if I should skip it or not. Maybe I will just skip it. But in case someone is interested, yes.
I'm sorry, I'm really unfamiliar with the mathematical languages.
Okay.
What is a Hausdorff space?
So Hausdorff space, so these are the technical things from topology. Basically, Hausdorff space, there are some spaces that when you can separate points, let's say formally, it means that if you have 2 points in the topology, you have a point here and a point here, you can draw a ball around this point and a ball around this point that are disjoint. So they are kind of topological spaces that are more or less, the points are distinguishable from each other. Because there are some other topological spaces more weird, that the points are kind of maybe too much close and you cannot do these things, for example. And they have these nice properties that sequences in these Hauser spaces, they converge to a unique limit and things like that. So let's say they are nice topological spaces in that sense.
And in that space, this AG is Cantor set.
Yeah. So with that topology, this A to the G, A to the set in particular, I think it works if the group is countable. For any countable group, it's going to be the Cantor space. Yes. Okay. Okay. Well, I will just keep this proof, but basically, what this thing says is that the action is continuous. So here, this lemma is mixing a little bit now what we discussed before, the shift action with the topology. It turns out this is a continuous function. And well, you can check later the proof if you want, but I think for now I will just skip it to go to other things. Okay, so let me present you now the formal definition of a cellular automaton. And as I said before, a cellular automaton is going to be a function of the configuration space A to the G with this property. There exists a finite subset of the group that we are going to call a memory set, and that function from this form. Now, this function doesn't go from A to the G, it goes only to A to the S, from A to the S, yeah, A to the S to A. And it satisfies this relation here. So this relation here, it takes a little bit of time to get used to what it says and what it means. Now I think with an example will be clear, but you can think of this local function as sort of the coordinate function of tau. Yeah, as you know, for example, when we have, if I write here, you see? So, for example, when we have these kind of functions from Rn to Rn, we can think of them as in this way. X1 up to Xn equal to, and then F1, and then again X1 up to Xn, and then Fn, X1 up to Xn. So this is what I mean, right, by the coordinate functions, right? So cellular automata are going to be, because there are some analogies between Rn and this A to the G. They are sort of Cartesian powers in a way. So think that mu is going to be the same. Always we're going to apply the same coordinate function all the time, mu, except that the input is not going to be necessarily the same. The input of mu has to be restricted. This denotes the restriction. The input has to be, so in a way, if we had here by infinite sequences instead of Rn, here we have, of course, by infinite sequences. So the thing is that when you put mu here, you have only the chance to see the memory set, because you have to be restricted to the memory set, and you have to be shifted by G in a way to see what's going on with the memory set. So let me show you some examples, and I hope this definition is more clear. So let's see an example over A to the Z. Let's take the group G to be Z, the alphabet to be 0 and 1, and S, that remember is the memory set, is going to be -1, 0. So this is a set of 2 integers, right? So this 0 and this 0 here are different, right? So this is the 0 integer, and this is just like a letter in the alphabet. Okay.
Sorry. S not be a subgroup of G.
No,
or not necessarily.
No, not necessarily. No.
Just
A subset. Yeah. That's something interesting, that S has to be a subset, but the important thing is that it's finite. Yeah, or to define this cellular automata. Yeah, it has to be finite. So we take -1, 0, And we're going to define this mu in this way. So a to the s kind of is just finite sequences now that are indexed like this, x minus 1, 0, because s is minus 1, 0. And let's say, suppose you take the maximum of these two, right? So it's a very easy function. If you have 0 and 0, the maximum will be 0. If you have 0 and 1, the maximum will be 1. You have 1 and 1, maximum will be 1, etc. Right? So this is just as an example. So the global function, sometimes they call this like the local function, and this is the global function, because actually there's like a one-to-one correspondence between this local function and this global. The way you apply it now is going to be as follows. So now tau is applied to bi-infinite sequences, and the thing is, you get another bi-infinite sequence. So the symbol here is going to be mu, but applied to -2, -1. And then the next symbol is going to be mu, but applied to x minus 1, x0. And the next symbol is going to be mu applied to x0, x1, etc. To progress like this. So in a way, what this memory set is telling you is that whenever you are in the bi-infinite sequence, look at the symbol that you are at the moment, and look toward to the neighbor of the right. And if you are the sequence, the neighbor of the right, right? So for example, here we are stepping at the -1 position. So look at -1 and the neighbor from this side, that is -2. And then look at this as 0, and the neighbor from this side is x minus 1, etc. And you progress like this. Yeah. Okay. So for example, here I have put a dot here just to say that this position of 1 is the 0th coordinate of the sequence. So if we apply specifically tau to this bi-infinite sequence, we get this bi-infinite sequence, and it's just applying this rule and taking the maximum. Because when we are here, we're going to be taking the maximum of, when we are here, we're going to be taking the maximum of 0 and 1, that is 1. That's why we put a 1 here. And when we are here, we're going to be taking again the maximum of 1 and 0, that is going to be 1 again. And then the rest of the entries of the bi-infinite sequence are going to be 0 everywhere. Okay?
Yes,
Yes.
that is synchronous, right?
Yes, exactly. So one of the key characteristics. So there has been defined also cellular automata that are asynchronous, and there's work related with that. But yes, sort of this more classical setting is synchronous. So this local function is applied everywhere at the same time. Yeah. Yeah.
Is this defined in the mathematical description?
Yes, it's synchronous.
But do you have to tell it separately? I mean, does the mathematical definition imply that it's synchronous?
Yes, exactly. So in this classical setting, yes. In this, let me go back. So in this kind of relation here implies that it has to be that wherever this is telling you sort of wherever you are looking at the image of the configuration, apply sort of at the same time mu. So kind of the fact that this has to satisfy this relation implies that it's synchronous. But I think there's some recent work like trying to develop more the theory of what would be what do you have to do to apply asynchronous, to apply something asynchronous. Yeah. Okay, let me go. Yeah. So this is I want to show you this picture because this is what they call sometimes a space-time diagram for cellular automata, for one-dimensional cellular automata. So here we have this is like the bi-infinite sequence, just the first row, right? So just with two colors. You can think of them, the white is 0, for example, and the black is 1, if you want, right? And then you have discrete time, because you can apply a cellular automaton. In this case, the cellular automaton is given by these rules here. In the memory set, in the previous example, it was -1, 0. In this case, it's going to be -1, 0, 1. And basically, what the rule is telling you is that, well, if you see this pattern updated by this pattern, if you see this pattern updated by this pattern, etc., right? So this is how the rule is defined. So if you apply it once, you go to the next row. You apply it twice, you go to the next row, and you can apply it like this. So you have sort of this time discrete dynamical system here, where the sort of you have one dimension that is this row, and then when you go down, you have the passage of time, discrete time. And so in particular, this is something called elementary cellular automaton, because when you have a memory set like this, -101, you call it elementary. And it's called Rule 90 because they have developed this system that if you see at the second row of this definition here, and you convert it into binary, so here we would have like 0, 1, 0, 1, 1, 0, 1, 0. If you look at that number in binary, and you can convert it to decimal, it turns out that it's 90. So it's called Rule 90. Okay. Well, there's another very famous cellular automaton called the Game of Life that probably you've heard of. It was invented by John Conway. And in this case, the difference with the Game of Life is that it's a two-dimensional cellular automaton. So now we have two-dimensional configurations like this. It's actually called a pulsar. I don't know why, but anyway, we call it physics now enough. And you apply the automaton, and what this is going to give you is another two-dimensional configuration, right? So now it goes from 2 dimensions to 2 dimensions, sort of. And the rules of the Game of Life are quite simple. Actually, if you check in Wikipedia or wherever, you have like nice names. Like, for example, you have the rules of survival. So if a cell is alive and it has like 3 alive cells, then it survives to the next generation and things like that. You have survival, you have death by overpopulation, you have how it's born, the cell, and you have death, I think. That's it, right? Kind of like that. But it turns out that we can analytically write the local function of the Game of Life, and it's like this. It's just it's a local function where now the memory set is like the square. If we see the two-dimensional thing here, sorry, it's like this square. For example, if we're looking at this cell, we take all these 8 neighbors and the cell here, right? So this is what I mean. -1, 0, 1 is like the Cartesian power. We take the channel, so it's all the possible pairs of this. So and you can define the local function of the Game of Life like this, by in these two cases. It's going to give you 1 if one of these conditions is satisfied. So basically, this is telling you here for example, if you have 3 neighbors that are alive, but the cell that you're looking is dead, then it will be born because it will become 1. And also, if you are alive and you have 2 neighbors that are alive, it will add up to 3, and you are going to be alive in the next generation. So all these rules are kind of summarized in this thing here. So what is interesting about the Game of Life is that it turns out to be Turing complete, which means that basically you can simulate a universal Turing machine using these rules. And it's many times used as an example of something that has simple rules, kind of a relatively simple, quite simple local rule, but that it can, a lot of complexity can emerge from it, right? Okay. Well, some of the basic theoretical results of, in general, of cellular automata. One is that the memory set that we have associated with a cellular automata or a cellular automaton is not unique, but every cellular automaton has a unique memory set of minimal size. So you can think of this as so the best analogy I can think is that, for example, let's say a polynomial function, you have x1, x2. You can think of it as, I don't know, x1 plus x2, for example. But you can say that this depends on 3 variables as well. Right? This would be correct. Right. Suppose it's a function, just x3 doesn't really appear. So this would be, let's say, a memory set in a way for our local function, but the minimal memory set are sort of the essential variables that that appear in the definition of the local group. You can always add other variables that they don't really do anything, but the essential ones, they are the ones that form the memory set of minimal size. Okay, and two interesting properties as well is that cellular automata are continuous in this discrete topology that we're talking about, and that they are G equivariant in the following sense. In the sense that if we apply the shift action to a configuration and then we apply the cellular automaton, is the same as if we apply first the cellular automaton and then do the shift action. So it commutes sort of always the cellular automaton. The cellular automata commute with the shift action. So this is, and surprisingly, it turns out that this is a characterization of cellular automata. It turns out that if you have a function from a to the g to a to the g, this function, a general function, this is going to be a cellular automaton if and only if it is continuous and it is G equivariant. It's the characterization. Here for this theorem, this is classically known as the Curtis-Hedlund theorem. I put here also Ceccherini, Silverstein, and Cornet because actually they proved it for a general group. Originally, Curtis and Hedlund had shown this for, I think, for the integers, when G was the integers. But there are some changes that had to be made to be proved for in general. So that's why I added the other guys. And also another interesting thing is that this theorem actually needs the set A to be finite. But if you want to drop that assumption, it's also possible. But instead of looking at the discrete topology, we have to look at something called the uniform structure of A to the G. And we have to replace here to be continuous by to be uniformly continuous, uniform continuous. If we want to work this theorem for infinite alphabets. In many cases, for multiple applications, finite alphabets A are used mainly. Okay, and a corollary of this result is that if we have a cellular automata, this is the notation that we use for the set of all cellular automata over the space A to the G. If it's bijective, automatically its inverse is going to be again a cellular automata. So this is a property that if you like algebra, maybe you are very much used to because, for example, think of linear transformations. If you have a linear transformation between vector spaces, and the linear transformation is bijective, automatically the inverse of linear transformation is again a linear transformation, right? The same works with group homomorphism, the same works with ring homomorphisms, with many algebraic functions. You have this characteristic that you take some function that satisfies some algebraic condition, and it's bijective, then the inverse function is going to satisfy the same algebraic condition. But it doesn't work with topological things sometimes. So for example, think of continuous functions. If you take a continuous function that is bijective, the inverse of the continuous function is not going to be necessarily continuous. Yeah, that's why you have we have the concept of homeomorphism, which is a continuous function whose inverse is also continuous. Okay. But in this case, despite we have two things, continuous and equivariant, it turns out that the topological space is so nice that everything works. And the inverse is all automatically a cellular automaton as well. Okay. To review some other results, this is something that I have been quite interested as well. That is, if you take different cellular automata, it can be the same, it can be different, tau and sigma, and you compose them, the result, the composition, is again a cellular automaton. So I think this is something quite interesting that maybe it has not. I mean, usually the most standard application of cellular automaton is to use the same one and apply it again and again. Use it like a discrete dynamical system.
It's like fixing the rules, and that will happen all the time.
Yes,
But doing composition would mean changing alphabet or changing rules or changing
rules. So yeah, we can take tau to be one rule and sigma to be another rule over the same configuration space, right? So for example, if we're in one-dimensional cellular automata, it has to be the other one-dimensional. We cannot, let's say, compose rule 90 with the game of life because they live in different configuration spaces, right? But we can compose rule 90 with rule 110, for example, of this elementary cellular automata, and it will give you something different, another cellular automata.
And this is still being applying this inverse of the cellular automata to still have this still being a cellular automata.
The inverse, yes. If it's
Even if
bijective.
there's composition between the
Yes.
cellular automata.
Yes. So the thing is that not all of them are going to be invertible, because not all of them are going to be bijective, right? Among all the cellular automata, you might have some that are bijective, some that are not bijective. And actually, to check that it's bijective is quite difficult in general. I think it has been shown that it's undecidable problem, actually, that given the local rule to determine if the global rule is going to be bijective or not, when you have you're in dimension 2 or higher, you have a set square or higher, it's really a very difficult problem to say if it's bijective or not, or if it's invertible or not. Yeah. Okay, so a consequence of this theorem is that when you take the set of all cellular automaton, this is going to be an algebraic structure known as a monoid, which is basically a set with a binary operation that is associative. And the group of units is basically the group of invertible elements. That is what I write here, the invertible cellular automaton. So these are two interesting objects, this monoid and this group. So I wanted to just show you a result that I managed to obtain related with this theory. For the general case, it is known, for example, that this group, going back, the group of invertible cellular automaton, when the group G is set, is going to be it turns out that it's a very remarkable group. It's not finitely generated. It's not finitely generated, but it's countable. It has actually an isomorphic copy of every finite group. You take any finite group that you want, there's an isomorphic copy inside here. And now they're very weird properties like that. Anyway, but this has been done particularly for the case of set. And even this basic result of being finitely generated or not has not been shown for other groups except for set. So what I did here is just show that this monoid is not finitely generated. I don't look at the group, I look at the whole monoid. And it turns out it's not finitely generated whenever the group satisfies this kind of technical condition. So we suppose that G has an infinite descending chain of normal subgroups of finite index. So this is actually satisfied by many infinite groups. What we want is sort of an infinite group that has a lot of normal subgroups of finite index. This is what we want. So if the group satisfies this condition, then this monoid is not finitely generated. But I suspect that maybe in general, whenever the group is infinite, it's not going to be finitely generated, but we don't know how to prove it. Okay. Yeah.
I mean, just
Yeah,
I'm
yeah.
not sure if I understood everything. One further slide.
Yeah, here.
So yeah, so you have this monoid, right?
Yes.
And if you restrict, if you take only those elements which are invertible, then they form automatically a group.
Yes, exactly. Yeah.
And if you ask what is the minimal set of elements which can generate the monoid,
Yeah.
it is this ICA or it is less than that?
No. So Actually, that's a good question. It's not like that. It's related. Let me write that because we didn't write it here. It's related. The minimal number of elements that generate sometimes it's written like this. It's written like the rank in this monoid or semi-group theory, and it turns out that usually this formula is satisfied. You take the rank of CA. I'm just going to write CA. This is going to be equal to the rank of ICA plus something rank that they call the relative rank. So the minimal number of elements that you need to generate a whole monoid is going to be equal to the minimal number of elements that you need to generate a group of units, this guy, plus this that we call the relative rank, that it's sort of the minimal number of elements that remain to generate the whole thing. Sort of. This formula is kind of telling you telling that in a way. So, for example, if this rank turns out to be infinite, because this formula holds even for cardinals. So if this is infinite, automatically this is infinite. Yeah. But if this is infinite, it doesn't necessarily imply that that this has to be infinite, because this could be finite, and maybe the problem is that the guy here is infinite. Yeah. So what I shown, what I work is sort of with this total rank, show that it's infinite, but it's still open the problem for this one here. Okay. Well, just to finish, there are a couple of technical. Maybe I will skip this as well, but I just want to tell you the story, the general story. There is these other classes of groups called amenable groups that coincidentally they were also introduced by John Boy Neumann. So John Boy Neumann introduced the concept of cellular automata. He introduced amenable groups in a different context. And it's related with this stuff, with groups that don't have paradoxical decomposition and admit other things. Paradoxical decomposition, sort of in the sense of this, if you've heard of this Tarski paradox, that you have a sphere and you can kind of decompose it and create two spheres that are the same. It's related with that, but for groups. So it turns out that the cellular automata are connected with these amenable groups, although John Boy Neumann didn't know. He just defined these two things. And well, this is perhaps the theorem that, well, this theorem here is called the Garden of Eden theorem. It has a very nice name, but basically what it tells you is when your group is amenable, then a cellular automata is going to be surjective if and only satisfies a condition called pre-injective. So it's just giving you another condition that surjective cellular automata satisfy. But what is very interesting, I think, is that actually amenable groups can be characterized in terms of those groups for which always the cellular automata satisfy this Garden of Eden theorem. Right? So you can say, you can add another definition of amenable group, saying a group is going to be amenable if and only if, for every finite set, every surjective cellular automaton over this configuration space is pre-injected. So it's a characterization of amenable groups in terms of the cellular automaton. And finally, there is this other two kinds of groups as well. There are some called surjunctive groups, because it turns out that in general, when you look at injective cellular automata, it turns out they are injective always implies surjective. But we don't know why this. So you look, take any cellular automata in general, check, see that it's injective, it's also going to be surjective. And these kind of groups are called surjunctive groups. So an open question, an open conjecture, is there is a conjecture that every group is surjunctive. So it's sort of a question saying that if it's a yeah, like an intrinsic property of cellular automata that injectivity implies always surjectivity. But we don't know why so far. Right? In all the examples, people have seen it's always the case. There's no counter example, but we really don't know why. And there's this very large class of groups called SOPI groups that sort of they admit local approximation by finite symmetric groups, and it has been shown that every SOPI group is surjunctive. It's sort of the largest class of groups that we are sure satisfy this property here. But it's kind of open still. So, okay, well, basically the conclusions of this talk, but what I just want to maybe remember at the end of this. First is that cellular automata are transformations of a configuration space defined by a memory set and a local function. These are the two properties, and they are applied synchronously everywhere. Traditionally, they are studied as a discrete dynamical system when the group is set or set square. And that they have also, there are also deep connections between cellular automata and group theory, like the characterization of amenable groups or the Gromov-Weiss theorem. Okay, so thank you very much.
So thank you, Dr. Alonso, for your very nice talk.
Thank
If
you.
anybody has further questions?
When you say that you study the theory, and only in a superficial way, what is the application of this?
Yeah, that's a good question. normally, the people, I don't know, at least in my point of view, people that we do theory, we don't really know how the application. But I mean, from the computer science point of view, I think they are very much interested in these questions of Turing completeness and stuff like that that are satisfied by cellular automata. From the modeling point of view, I know there are some natural phenomena, for example, that have been modeled by cellular automata. Sort of, the thing is, the ingredients that you need are sort of, you need kind of a discrete space, because they work on this pro-discrete topology, which is sort of discrete. So you need a discrete space, and you need that the evolution of the space, it's applied synchronously at the same time everywhere, and always using the same local rule. So it doesn't matter where you are in your discrete space, you have to apply the same local rule, depending on a neighborhood, let's say, on the space. So in this kind of phenomena that behave like this, they can be applied.
I have a question. First, for example, when doing the simulations in cellular automata, you do something like continuous periodic boundary conditions or something like that. This is the case of thinking of an infinite ace or not, or
Yeah.
just skip that.
So I think this periodic boundary condition under this is sort of when you want to look at a finite case more. Because so for example, because of course it's very difficult to have an infinite representation actually of something. So if you're only restricted to a finite thing, you have to ask, so what's going to happen in the boundaries, sort of. When you arrive to the boundaries, how you are going to apply the rule there. So sometimes they have the periodic boundary condition, is sort of maybe the boundary here is connected with the boundary here, and you see the neighbors like this. Or I think there are also sometimes that they say, well, when you're in the boundary, you do have no neighbors. So you kind of have to apply or no neighbors on one side at least. And you have to apply the rule in a different way.
Yeah. But it doesn't, it doesn't cause problems about definitions of infinite sets or stuff like that?
Yes. So you mean for the theory and all this?
Yeah.
Yeah. So the periodic boundary condition, I think it will cause there's no problem, because you have to take the appropriate group that you are working with. So sort of, if you take like a cyclic group, let's say set n, I don't know, set 10, for example, it means sort of you are in a one-dimensional space, but you are cyclic. So you are like this, because after number 9, it's number 0 in the cyclic group. So you have in this way sort of a periodic boundary condition. So if you take the appropriate group and you have a setting like this, then all the theory goes well. Yeah, all the theory goes well. Yeah.
Okay. And this you're saying the theories we have presented will remain unaffected for the finite systems also.
Sorry, the
The
what?
theories we presented will remain unaffected for the finite systems also.
Yes, exactly. Yeah. Actually, they will be simplified a lot for the finite systems in many cases. Because when the group, where sort of your space, the group that you are is finite, in this case, the topological aspects, they become almost basically trivial because now you have discrete topology and there is still some interesting stuff, but it's very much simplified when it's finite. Yeah.
I don't know if it is a problem, maybe it's not even a problem, right? But in principle, if you have a finite group, then your memory space can be the whole group.
Yes, actually, yes.
So then it's,
Yeah, definitely, yeah. So yeah, the memory set can be the whole group, but the minimal memory set might change. So you might have minimal memory set that is very small, and the maximum size of the minimal memory set would be the whole group. Yes.
you might be able to stick only in cellular automaton. Well, that's maybe an interesting question, but if you restrict yourself to finite, well, to memory sets of a certain size, so you classify yourself.
Yes.
So does this give you some?
Yeah.
Do people work on this?
So actually, I did some work on that. I think not so many people have done so much work on that, but I did some work on that during my postdoc. And one of sort of maybe the nice things we got related with that is that if you can have, again, the monoid of all cellular automata, but if you suppose that G is finite, and then suppose you want to take a generating set for this monoid. So we want to take a set of cellular automata such that every cellular automata here can be expressed as a composition of these guys. So if we have a generating set, at least one element in your generated set, its minimal memory set has to be the whole group. So at least you need, I mean, in other words, you cannot generate the whole thing using always small memory sets. We can say it that way. You will always need at least one guy whose memory set is the whole group, the whole finite group.
I have another question.
Yes.
Do you know about interesting infinite groups which are not abelian?
It's another vegan? Yeah, that's an interesting question. I mean, so in practice for the application, something like that, I don't know. That's a good question. I'm not sure. Well, I know there has been, for example, there is some work done on the free group. So, for example, the free group on two generators, it means basically you take all words. Say you have two letters A, B, and you have all possible words with A and B, and the operation is concatenation of these words of all different finite words of different size. And like this, you get something called the free group on two generator. And this is not abelian, and it's actually kind of a complicated infinite group. And there is some theoretical results related with this group, but applications and practical stuff, I don't know. Yeah, it has a shift action. Yes. But yeah, it's not abelian. Yeah.
Other questions, anyone? Let's wait 5 minutes to see if they. Okay, if not, then thanks. Thanks again. Okay, so we're not having seminar next week or until 2 weeks. Okay. By the way, tomorrow's Gustavo's talk is shifted for next Friday because he's going to give a talk also at the Fondo de Cultura Económica at 7. So, okay. Okay, thank you.
Thank you. Gracias. Gracias. Muchas gracias. Gracias. Ya. Quitar aquí.
¿Te ha ido?
No, pues nada más quiero recuperar la memoria. Pero, ahí.